Welcome. We're going to look at some things with the graphs of rational functions. Rational simply meaning a fraction as part of the equation. And we're going to start with very specific end behavior format. So the way that you're going to write end behavior, well, actually, let's actually do a graph here. I'm going to do an asymptote here, where x is equal to 3. And I'm going to have the graph go as it's loath to do so, like so. Right, so now we're going to do end behavior. And this is how you're going to write it. As x approaches negative infinity, comma, the function of x approaches 0 from, as we go that way, from the negatives from below. Let me do a second one of these, and then we're going to analyze what I'm writing. As x approaches 3 minus, and that minus means approaching it from the left, the function of x approaches negative infinity. I think I'm going to rewrite that in black. And the reason I'm going to do that is I'm going to show where these are on the graph by virtue of color. Okay, so the blue is as we're going this way. So as the x values, here are the x values, and as the x values are going that direction, because you see there's an arrow here, as the x values are along the y-axis or x-axis are going that way, what is happening to the function? The function is getting closer. It's going up like this. It's getting closer and closer and closer to 0. So as the function goes out towards negative infinity, the function gets closer to 0, but it gets to 0 from down, from below. That's what the minus means, coming up to it from below. The second one now, I'm going to have that in black, we're coming along the x-axis this way. And as it approaches 3 coming from the negatives or coming from the left, the function of x is going down here and is going down and down and down and down and down forever and forever and forever and forever. And that's why it's negative infinity. Now let's use red for the next one. For the next one, because we see that this is going this way, we're going to approach x coming from the right side. As x approaches 3 from the right side, the function is going up. The function of x, or the y values, are going up to positive infinity. So that makes sense. What you're looking at is what is the x doing, and then what is the y doing. Okay, now let's use the last color I have available, green. As x approaches infinity, which means now we're going out this way. Well, let's look at the function. The function here is going that way, but it's actually getting closer and closer to 0. It's getting closer and closer and closer to 0, just like over here, it's getting closer and closer to 0. But now the function of x is getting closer to 0, coming from the top, from the positives. Okay. This is what you have to do for end behavior. And this is the format that it has to be written as. The only exception I would accept is if somebody started with the function first, and they did the function of x. Let's take the first one there. The function of x, the top one, the function of x is approaching 0 from the negative as x is approaching negative infinity. Now, only alternative allowed. Only alternative allowed. I don't recommend to do it just so you don't mix things up. Okay. And the textbook's showing it this way, so do it that way. Notice something else here. Notice there's a comma here because in the English language, you have a clause followed by a statement. So you have to actually have put a comma in it. In this other one, you don't have to do that. In fact, you shouldn't do it. The function is approaching 0 from the right as x is doing this. That's the way you speak it, and you don't speak it with a comma type of thing in your sentence or in your speaking. So there's no comma in that second one, but there is in the first. So put it that way. And so must follow this format. And I'll grin and bear it if you do the other one, but I won't like it. So do this one. I won't grin, I'll just bear it, actually. So must follow this type of format. Now let's take a look at some asymptote things. All right. We're going to be analyzing vertical, horizontal, and slant asymptotes. And first, vertical asymptotes are frankly relatively easy to do and figure out because we're simply finding out what makes a 0 on the bottom. What do I mean by that? So in this one here, let's go ahead and factor there. That's plus 3. Now, because these cancel out, we have 1 over x plus 3. So what that means, this x plus 3 equals 0, x equals negative 3. That is the asymptote. Now, mathematically, I'd like to say x is not equal to negative 3, but since the point of it is to actually graph that line, we'll graph the line where x is equal to negative 3. We just are not allowed to touch it. We cannot have the graph go to that. All right, so that's one major part of this is how you get the asymptote. The second part of this is the whole, or what's called the point discontinuity. Discontinuity. And the point discontinuity is a point in the graph where it's not continuous anymore. It jumps over it, goes around it, or actually doesn't even do that, it just stops. And you go like, what do we do now? And then it picks up on the other side, almost as if it was never there, except that you can't touch that point discontinuity. And the whole is whichever part was canceled out, factor that was canceled. The factor that was canceled, if there is one. There might not be one. If there is one. If there isn't one, then there's no whole. That's simple. There just isn't one. Then you don't have to worry about it. But in this case, we have x minus 2. Make it equal to 0, so you can say x is equal to 2. So that means wherever the graph goes at 2, you have to put a hole and then have the graph continue. Okay, so that's where x is equal to 2, you have to put a hole. So now, having said that, let's actually graph this. The way this would graph would be approximately like this. Ooh, notice I put a hole. That's the idea, I put a hole. The asymptote is the part, the x values it cannot touch. The hole is the one point you have to jump over. I suppose I should do this and this to show that's supposed to be 2 there. So, I get that in blue over there, so let's do it in blue. That's the hole. Okay, our point discontinuity. Make sure you're comfortable with recognizing that and using it when you need to use it. Okay, now next, let's take a look at horizontal asymptote. In the horizontal asymptotes, you are looking at the degree of the numerator and the denominator. If n is less than m, meaning the degree on top is smaller than the degree on bottom, and automatically it's y equals 0. So an example here is not 6 and 3, but rather 3 and 4. So because 3 is less than 4, therefore, and see that's the math and scientific way of stating, therefore, y equals 0 for horizontal asymptote. That means in the graph of it, that means that this part, the graph wouldn't touch, which is what you often see. You often see it going like this and going like this, and it gets closer to 0 and doesn't touch 0. That's y equals 0. Now, different if they're reversed. Here's 4 and here's 3. So here 4 is greater than 3. That's n greater than m. That means you have a slant asymptote. Okay. And that's coming up on the next page. So wait a moment and we'll see what to do with slant asymptotes. If they're equal, I suppose it's not that I should do, it's the equal. If they're equal, you calculate it by using the a and the b. Here's where the 6 and 3 would now come in. A is the coefficient on top and the b is the coefficient on bottom. 6 over 3 is equal to 2, so y equals 2 is the horizontal asymptote. Okay, and graph-wise, that would look 1, 2. So your graph might be something like this. So instead of getting closer to 0, it's getting closer to 2 from all the sides. I just can't quite get away without putting an arrow there. So you have 3 possibilities where the coefficient, the larger degree is on the bottom, the larger degree is on top, or both degrees are equal, in which case you use the coefficients to determine what your asymptote is, your horizontal asymptote. Well, I promised we'd look at slant asymptotes, so let's do exactly that. So here on this next page, so in a slant asymptote, it means there's no horizontal asymptote. And I'll show you what this looks like in a moment. The way that you figure this out is that you do division. So we are going to do either synthetic or long division, and we're going to find the equation that way. So I'm going to do x goes into x squared plus 4. Well, x, in order to make x squared, is going to be x. So x times x is x squared. So I subtract that, and I get just 4. Well, x can't be made into 4. Therefore, this becomes y equals x. So what we do is we do y equals whatever the result is. So in this case, there would be an asymptote at y equals x, which is graphed as that inverse line, diagonal, y equals x. And then once you graph the points on this, okay, you're going to get something that's probably like this. Notice it does a very interesting type of weird graph, because here also at the same time of that, we have a vertical asymptote of x equals 0. So x equals 0 cannot be touched by it, and neither can y equals x. That one I should put dashed lines. This is an asymptote. It's not required, but pretty normal to do them in dashed lines. That's the x equals 0, and that's the y equals x. And those are asymptotes. So the slant asymptote. Now let's do a different one that's going to be a little more than just x equals 0 or y equals x. And that's this one here. Now on this one, I'm going to do the same concept, same thing. I could also do this in synthetic division if I wanted to. In fact, why don't I do that, this one in synthetic division? Because it really doesn't matter which way. I'm going to use the opposite sign from this. And then I'm going to have 1 minus 5 and 2. So bring the 1 down. 3 times 1 is 3. Minus 5, that's minus 2. 3 times negative 2 is negative 6. That's negative 4. But you know what? This just doesn't matter. Here's the thing. Back up here, I got the 4, and I just said stop. And I only use this because in doing slant asymptotes, you just throw away any remainder. You just don't need it. It's useful algebraically, but it's not needed for graphing of this. So now I have this, because it was a 2 degree, this becomes a 1 degree, x, 1x to the first power minus 2. And of course, it's y equals that. So that is going to be our asymptote here. Yeah, the approximation of where that would be. And now this one, well, there could be very different ways it could be. It could be like the other one was like this, but I believe this one is actually going where let's see. Oh, we also have to account for the fact that x cannot be equal to 3 or is equal to 3. So the asymptote, the vertical asymptote, make that more readable. Asymptote, x minus 3 is 0, so x equals 3. 1, 2, 3. So it could be that it's coming this way and down here, but I believe in this one it's not. It's going to be, and this is going to be a weird look, but this is what sometimes happens. It's going to be like this. Interesting. So it hugs the asymptotes. They'll get closer and closer. They'll get closer and closer to x equals 3 and closer to y equals x minus 2. And so an interesting view or an interesting type of graph for flash nodes. And the slant asymptote, really what you just do is with a long division or synthetic division, and it's not too hard to find that. And then instead of the asymptote being a vertical horizontal, it's actually a diagonal, or as we're called in this context, a slant asymptote. Well, I hope this has been helpful, and thank you for watching and listening.